The solid propellant booster propels the vehicle, transitioning rapidly to hypersonic speeds and achieving a stable low exoatmospheric glide path. Or how the vehicle utilizes advanced computational telemetry loops to continually alter its flight path, rendering standard ballistic tracking algorithms obsolete. The key is the thrust vectoring capability, allowing the hypersonic vehicle to instantly rewrite its trajectory upon detecting the radar lock. With the clamps secured, the raw material loading phase is complete. We now transition to the active computer-controlled machining stage.
The process ensures energy density optimization, achieved through the precise addition of calibrated metal powders.
The vacuum degassing process is critical, eliminating internal air pockets that could cause catastrophic structural failure during missile ignition. The critical role of vacuum degassing in eliminating internal air pockets that could cause catastrophic structural failure during missile ignition. We are outlining the cross-linking of the polymer chains that gives the solid propellant its rugged structural properties. The internal geometry determines the thrust profile and acceleration parameters of the hypersonic weapon. This completes the chemical mixing and casting.
The structural loads the vehicle will endure at hypervelocity speeds require an unyielding mechanical connection between sections. The internal locking mechanism designed to distribute aerodynamic shear stresses evenly across the entire length of the fuselage. This sophisticated thermal bonding agent creates a flawless seal, specifically engineered to withstand the extreme friction of Mach 13 flight. The internal locking mechanism is designed to distribute aerodynamic shear stresses evenly across the entire length of the fuselage. This underground facility represents a massive leap in streamlined weapon assembly, utilizing complete logistical automation.
The calibration bed ensures the strict geometric tolerances required for stable atmospheric flight paths at high velocities. The complex computational requirements needed to calculate flight metrics continuously while operating at extreme hypervelocity speeds. The hardened semiconductor architecture is required to resist intense electromagnetic interference and high thermal radiation profiles during atmospheric penetration. The internal shock-absorbing mounts provide critical resilience. They are specifically designed to withstand the extreme G-force loads experienced at hypersonic speeds. The multi-constellation satellite tracking software is designed to supplement the inertial navigation unit and minimize target deviation over long distances. The real-time operating system algorithms command the thrust vector nozzles and control surfaces during non-ballistic maneuvers. The intense engineering challenges associated with stabilizing the weight distribution of the forward section to maintain aerodynamic control at hypersonic velocities. To counter the extreme shearing forces and structural vibrations of atmospheric reentry, these rigid load-bearing connections are essential for evasive maneuvers. These dual redundant modules feature hardened circuitry, resistant to the extreme thermal ionization profiles experienced during hypersonic flight. The advanced ceramic material designed to withstand temperatures exceeding 2,000 degrees Celsius caused by atmospheric compression during Mach 15 flight paths. How even a sub-millimeter deviation in surface uniformity could create turbulent airflow patterns and disrupt the vehicle trajectory at extreme speeds. The engineering behind the movable nozzle assembly enables the Fattah-1 to perform sudden maneuvering adjustments both inside and outside the dense atmosphere. The immense torque requirements necessary to alter the exhaust vector against thousands of pounds of thrust pressure during the high-speed boost phase. The specialized composite materials of these fins are designed to resist extreme thermal ionization profiles and the high mechanical drag forces encountered at hypersonic speeds. The dual redundant digital control bus designed to transmit instantaneous trajectory corrections from the main guidance computer to the flight control actuators without lag.
The synchronized motion of both the aerodynamic fins and the thrust vectoring nozzle ensures stability when transitioning between different atmospheric density zones.
Glass-core fiber cables provide light-speed data transmission between the forward navigation computers and the rear control surface actuators without suffering from electromagnetic pulse degradation. Maneuverable. Their capability to control pressurized gas flows perfectly at sub-zero temperatures. This validation step, the complex multi-pin interface, feeds real-time targeting coordinates from external computers directly into the flight memory, right up to the millisecond of launch. The specialized outer skin coating must perfectly isolate internal guidance electronics from external battlefield radar distortion and deliver the complex logistical steps required to move a 12-meter missile assembly through restricted underground pathways without disturbing calibrated internal guidance networks. The structural design of these deeply buried networks, which are engineered to withstand multiple high-yield impacts while maintaining full operational transit capabilities. The heavy lifting framework utilizes specialized safety links, designed to secure multi-ton loads during vertical alignment shifts. The strategic isolation of these deeply buried silos safeguards the weapon from external detection, ensuring launch readiness even under extreme combat scenarios. These permanent umbilical connections continuously monitor solid propellant temperatures and system battery status while the weapon remains in long-term storage. Strict multi-layered validation protocols are required to unlock the primary computing systems of the weapon, ensuring absolute protection against unauthorized deployments. The system injects complex orbital and atmospheric vector calculations into the guidance unit, charting an unpredictable path that avoids tracking radar networks. The command center is initiating the cryptographic handshake. These military-grade protocols highlight the connection's high resistance to external noise and intercept attempts. Analyzing the military-grade cryptographic protocols, the connection shows high resistance to electromagnetic noise and intercept attempts. Secure link established. The critical importance of keeping the solid fuel compound within a narrow temperature window to guarantee optimal burn rates and uniform thrust parameters. These multi-ton mechanical restraints secure the launch platform during peacetime storage, but must clear the path cleanly within fractions of a second when launch sequences are initiated.